And welcome to High School Physics Explained, and today I'm going to do a video on JJ Thomson and his discovery of the electron. And as I go through it, I will touch on a little bit of the history of the cathode ray tube and the controversy that it initially created. I'll touch also on the behavior of charges in both an electric field and a magnetic field and how all of these things contributed to the discovery of the electron. So let's get started. So in 1855, Geissler, who was a glassblower by trade, developed the vacuum tube. So he was able to produce a tube made out of glass and remove a significant portion of gas within that tube. And he embedded within that tube two terminals. So he was able to connect it to an electrical supply or a battery and allow a current to pass through it. And he noted that it actually glowed when he placed a voltage across it. A couple of years later, 1858, Plücker was able to produce the same effect in what was known at the time the Geissler tubes, and he was able to vary the pressure within the tubes, in other words, vary the amount of gas within the tube, and he noticed that it emitted different amounts of light, but he also noted that the light could actually be deflected by a magnet. So he supposed that whatever was in the tube was electrically charged because it was known at the time that an electrical charge could be deviated by the presence of a magnetic field. In 1875, an English scientist by the name of Crookes believed that these particles that were within this Geissler tube, which is now known as a cathode ray tube, were negatively charged particles. And he noted that if you change the anode or the cathode, it wouldn't affect the actual light that was emitted. And he surmised that there was some sort of negatively charged particle emitted out from the cathode and travelled in straight lines to the anode. And he did a number of experiments that helped him predict that it would be a charged particle of some sort. And two types of tubes that he developed, one was the Maltese Cross. And so what we have here is a cathode emitting these cathode rays, and they would strike this Maltese Cross. And the fluorescent end would glow where these cathode rays would hit, just as what Plücker had seen, but the Maltese Cross created a shadow on the end. And what Crookes surmised is that these particles travelled in straight lines. The fact is that these particles were blocked by this Maltese Cross and hence produced a shadow. Another thing that he was able to produce is he was able to produce this paddle wheel setup. Now, ensuring that this setup was completely level, he noted that when he applied a supply to it, an electrical supply, he'd get his cathode rays being emitted, and as they were being emitted, the paddle wheel would start to move. So now all of a sudden, this paddle wheel was moving due to some sort of a collision with these negatively charged particles that Crookes believed. So Crookes was a strong proponent that these particles were negatively charged particles with mass. Now, there's no conclusive evidence at this stage to suggest that he was correct. And so in the 1880s, other scientists, interestingly enough, on the other side of the English Channel, did similar experiments on the cathode rays, but came to different conclusions. So Heinrich Hertz tested the cathode rays. He surmised that, well, if they are negatively charged particles, then they should be deflected by an electric field. But he failed to deflect them. He did not see any deflection. And so he concluded that they were a form of light. And so he concluded that they are some sort of electromagnetic radiation. At the time, also an area of research after Maxwell's predictions of electromagnetic radiation. Philip Lenard, a Frenchman, also looked at these cathode rays and he fired them at gold foil. Now, in this case, the cathode rays passed straight through them. So again, he was of the opinion that these cathode rays were not forms of matter, but were some sort of electromagnetic radiation. So here you can see there is a little bit of discussion in Europe as to the nature of cathode rays. Were they particles, as Crookes believed, or were they forms of electromagnetic radiation, which Hertz and Lenard suggested? So none of this was conclusively decided upon until 1897. And in 1897, a British scientist named JJ Thomson set up an experiment to help determine the nature of these cathode ray tubes. And so here is JJ Thomson at his work, and here is a picture of the tube that he looked at. And you'll notice it has a number of features. It has a cathode, and that cathode emits the cathode rays. Then over here, you'll notice I have a series of anodes. And these anodes, being positively charged, cause whatever these rays were to accelerate. So because they're positively charged, and the view was that they were negatively charged, they accelerated through these anodes. And if you look very carefully, you can see there's a slit here. So what happens is, what JJ Thomson was able to produce was a very narrow beam of cathode rays. Then over here you see another set of plates, and in this case JJ Thomson was setting up an electric field. So by setting up an electric field, he was hoping to deflect this particular beam either up or down depending on the polarity of this electric field. So here's a diagram of his setup, and as you can see, what we have here is my cathode over here, my anode over here, and the anode having a hole through the actual terminals meant that our beam is collimated. In other words, we've got this narrow beam of cathode rays, and he noticed that they started to curve upwards, and they do curve upwards because of course there is an electric field at play here, and so their charged particles are accelerating in the vertical direction due to a force that they're applied, which I'll discuss in a moment. And the fact that they deflected towards the positive plate suggested straight away that whatever the cathode rays were, they were certainly negatively charged. Now, only a moment ago I mentioned that Heinrich Hertz was unable to deflect them through electric field, but it was only a few years that took place that allowed JJ Thomson to develop a much better and more accurate way of measuring the deflection of electric field. And so, because of improvements in technology, he was able to deflect these cathode rays through the use of an electric field. So let's discuss the nature of the movement of this negatively charged particle through our electric field. And as you can see, I've set up here an electric field as shown as the lines go from a positive plate to a negative plate. Now, how did he actually set this up? Now, a quick revision. We should already know that an electric field is determined by the amount of force per unit charge. That is how we define an electric field. It's the force per unit charge. And as you can see, the unit is usually written as newtons per coulomb. But of course, how does he actually set this up? JJ Thomson sets this up by setting up a potential difference across this. And so we have a certain voltage. Now, what is voltage? Now, voltage is equal to the amount of work done per unit charge. That's a definition, if you remember your work from maybe earlier studies, is that the definition of voltage or potential is the work done per unit charge, which is the same way as saying the amount of potential energy per charge, or energy per charge. But what is work? Now, work is when you apply a force on an object over a certain displacement or distance. And in this case, the distance is the separation here between these gaps. So this is my distance over here. And of course, the voltage is this work done per unit charge. So now all of a sudden, if you look very carefully, I have F over Q here, and F over Q is equal to the electric field. So the electric field multiplied by the distance between the plates gives me my potential difference. Or better way of saying it is that the electric field can also be determined by the amount of voltage you apply over the distance, or the distance between the plates. And so our units for electric field can not only be newtons per coulomb, but they can also be volts per meter. And so very simply, what JJ Thomson did was apply a voltage which he was able to regulate and ensure that these plates were close enough so that the electric field was strong enough to deflect this negatively charged particle. And of course, this negatively charged particle is experiencing a force, in this case, in the upward direction. Now, it's moving also, of course, horizontally at a constant rate. And you should know that if an object has horizontal motion, and then it has an accelerated motion that is perpendicular to its constant motion, what you basically get here is projectile motion. And in essence, that is what happens to my charge. They actually undergo projectile motion, and that's because we have a net force acting in the vertical while the object is moving horizontally. And of course, in reality, of course, my projectile motion for this case would be actually much slighter. And in the case of JJ Thomson, this would cause this to bend, and therefore, as a result, if we just go back to the diagram here, it would deflect and reach up here. And the amount that would actually be moving up here is determined by, of course, the force that's applied here. And so he could measure that distance and notice that changing the voltage would change the amount that the deflection occurred. Before we go on about what JJ Thomson did that was so different to the work of previous scientists, we need to quickly touch on the nature of the motion of a charge in a magnetic field. So in this case, we already know that we have a magnetic field like so, and we also, of course, have our moving charge, which we know already is negatively charged. If we have a moving negative charge, then the conventional current is actually in the opposite direction. And so using your right-hand slap rule, you should know that the force that is going to be applied will be applied in this direction. But that, of course, will cause my charge here to change direction and now head downward like so. But the force will again, in this case, be perpendicular to the motion, and so will go in this direction. And so what you in essence get in this case is that my particle will actually follow a circular motion because of the force always being perpendicular to the motion of my negatively charged particle. And so in essence, what you get is a force that is due to a charge, and that formula that determines the force that is experiencing is equal to Q, V, and B, where Q is the charge, V is the velocity of my particle, and B is the strength of the magnetic field. The larger this magnetic field is, the tighter this is going to turn. And so what we end up getting is we have circular motion. And I'll touch on that in a moment in terms of the significance of that. What JJ Thomson did was so different was he said, well, okay, we know that a charged particle, our cathode ray, can be deflected by an electric field and it can be deflected by a magnetic field. What he did was he did both. So he was able to apply a magnetic field and an electric field in the same region of his cathode ray tube. And so as a result, he was able to apply an electric field that caused the charge to experience a force in the upward direction. But at the same time, he was able to apply a force due to the magnetic field that was in the opposite direction. And because he was able to determine the electric field by just changing the voltage and the distance between the plates, and because he was able to determine the magnetic field by changing the strength of the magnets, he was able to apply those fields so that the forces that these charges experience are equal but in opposite direction. And as a result, my charged particle, my cathode ray, would remain undeflected as it passed through both fields. So let's have a look at that mathematically. So first of all, we know that we have the force due to the electric field and the magnetic field being equal. Now we know that the force due to the magnetic field is equal to QVB. We also know that the force due to the electric field, which we've already established, is simply equal to EQ. Now, of course, what he can do now, because the two are now equal, because the forces are equal, he was able to discount or remove the value of the charge in this situation. V, of course, is the velocity of the cathode ray, And you can now see that is simply equal to the electric field strength divided by the magnetic field strength. As I've said, JJ Thomson already knew the electric field. He already knew the strength of the magnetic field. So now he was in a position to work out the velocity of this cathode ray. And he did work out the velocity. And he got a value of approximately 1 by 10 to the power of 7 meters per second. So that's pretty good. But can you see the significance of this? The most important thing here is not what the value is, but what it isn't. It isn't c. It isn't the speed of light. And because Maxwell had already confirmed that the speed of light or the speed of electromagnetic radiation is a constant value, namely 3 by 10 to the power of 8 meters per second, the fact that this velocity is not that value automatically settled the debate. Whatever the cathode rays were, they were not a form of electromagnetic radiation because they were not traveling at this particular speed. They were traveling at another speed. So that is the first part of JJ Thomson's significant contribution. But he goes further. So now JJ Thomson already has established the velocity of his charged particles. And what he does is now just removes the electric field and measures the amount of deflection in a different tube where he was able to measure the amount of turning within a magnetic field. And so the first thing he does, he understands that this is going under circular motion. So he understands that there is a centripetal force at play. And of course the centripetal force is equal to mv squared over r. But we know that the force that is occurring here is the force due to the magnetic field, and we already know that is equal to QVB. But the thing is, the two are exactly the same. The force on a charge in a magnetic field is actually the centripetal force of that charge in the magnetic field. So what you now have is you have QVB equaling mv squared over r. So these two values are exactly the same. We can now rearrange this and clean this up. The first thing you need to see is that the v's cancel. The second thing is we can now rearrange this, and this is what JJ Thomson did, because what he was interested in was the ratio of the charge to mass ratio. Why? Because it was an actual value, an empirical value that was determined for a number of substances. So the charge to mass ratio was known for hydrogen, for example, which we now know is simply a proton, and many other particular atoms as well. So they weren't able to work out necessarily a charge, but they were able to work out in a number of experiments at least the mathematical ratio between the charge and the mass of whatever object that they were studying. So if we clean this up, you can see that the charge to mass ratio ends up equaling V over BR. Now, remember, V was already determined by JJ Thomson by equating the force due to the electric field and the force due to the magnetic field. We already have the magnetic field, but by measuring the amount of curvature, and remember what the charges do is that they cause a glass screen to fluoresce, he was able to determine the actual radius of the curvature of this particular cathode ray. So he was able to determine V as well. And as a result, he was able to work what we call the charge to mass ratio. It's equal to V over BR. And what he discovered was this. JJ Thomson was now able to calculate the charge to mass ratio of this unknown cathode ray particle. It was already known for the hydrogen atom, which at that time was the smallest known atom around, which we already know that because it is made up of only one proton. And what he discovered was this. He discovered that the charge to mass ratio of this cathode ray was 1800 times bigger than the charge to mass ratio of a hydrogen. 1800 times. So that basically means that either A, the charge on my cathode ray is 1800 times bigger than my the charge for my hydrogen. Now that is one option. The other option is that the mass of my cathode ray is 1800 times smaller than the mass of the hydrogen. Now clearly, the fact that the cathode ray could not be deflected by electric fields suggests clearly that the charge is not 1800 times larger than the charge of the hydrogen atom. So the only possible solution is that the mass is 1800 times smaller. Now that in itself is pretty significant. So here we have the hydrogen atom, which at that time was to be known the smallest form of matter, and here we have a cathode ray, which we know to be a particle and is 1800 times smaller than the hydrogen atom. So JJ Thomson correctly surmised that we have here a new particle, and this new particle is 1800 times smaller than the proton. Now the proton was discovered, or at least understood, in the early 1920s, but at that time, of course, we know this as to be hydrogen. Secondly, whatever this particle is, it is also negatively charged. It has the same size as our hydrogen ion. And so what JJ Thomson said, well, we have a new particle and I'm going to give it a new name. And the new name is based on the Greek word for amber. As we know, amber is a petrified tree sap. And the name for amber in Greek is electros. And hence we have the electron. So here's the discovery of the electron. By JJ Thomson's work of cathode rays, by being able to deflect it with electric fields and magnetic fields accurately, and thus measuring also the radius of curvature of our cathode ray in a magnetic field, he was able to show conclusively that this particle that the cathode ray is made up is the electron. Interestingly enough, we now know the actual ratio of the mass between the hydrogen nucleus and the electron, and that value is 1836. So if you get the rest mass of a proton and divide that by the rest mass of our electron, you're going to get 1836. That's pretty close to what JJ Thomson worked out in the late 1800s. Well, I hope that's helped you understand the discovery of the electron and a little bit of the physics behind it. Please like this video if this has helped you, and by all means, please share with your peers if you think this video is useful for them. If you want to see more of my videos, please subscribe and share as well. Thanks for watching. Bye for now.